Hello everyone, my name is Dmitry Fedorov. I'm a postdoc at General Atomics and Argonne National Lab. And today I'm going to talk about Initio Molecular Dynamics on quantum computers. First, quick introduction to Initio Molecular Dynamics. We need to solve the time-dependent Schrödinger equation for the total molecular wave function, which depends on electronic coordinates, nuclear coordinates, and time. And we begin with the solution of the time-independent Schrödinger equation, which is not solvable exactly. So we apply Born-Oppenheimer approximation to separate electronic and nuclear degrees of freedom. And we can do that because electrons move much faster than the nuclei. And after we do the separation, we can solve the electronic Schrödinger equation to find the potential energy surface, which is energies for each nuclear coordinate, and we can use these potential energy surfaces to propagate the nuclei and solve the time-dependent Schrödinger equation for the nuclei. And in this project, we use the classical limit for the nuclei propagation. So the Schrödinger equation reduces to the classical equations of motion. And in IMD simulations, the bottleneck is the calculation of electronic energies and forces. So classically, how do we do this on a classical computer? So we usually begin with the mean field approach, such as Hartree-Fock, which is ground state electron configuration, and then we can use post-Hartree-Fock methods to recover so-called correlation energy with methods such as coupled cluster, configuration interaction, some multi-configurational methods, or full configuration interaction, which includes all possible excitations and represents the exact solution of the Schrödinger equation for a given basis set. The problem here is that for a classical computer, is the number of possible configurations grows exponentially. And so the promise of the applying quantum computers to quantum chemistry problems is that it is natural to represent quantum system on a quantum computer. So with classical bits, for n-bit system, you have 2 to the power of n possible states, and it's always in one of those states. For a quantum computer, you have qubits that can be in a superposition of all possible states, and that allows you to take advantage of it, because for a quantum system to represent it on a classical computer, just to store the wave function for 50 qubits, you would need 16 petabytes of storage. So quantum chemistry on quantum computers. We begin with fermionic problem. We form the electronic Hamiltonian in second quantized form. Here, H, PQ are the 1 electron integrals, and H, PQ, are 2 electron integrals, and A and A dagger creation and annihilation operators. So we map this fermionic problem onto qubits. There are different ways of mapping, but we always end up with this, with a Hamiltonian in this form, which is basically a sum of the products of the Pauli matrices with the coefficients that depend on the 1 and 2 electron integrals that are computed classically. And when we apply the unitary coupled cluster with singles and doubles, which is a unitary analog of the classical coupled cluster method, which creates these excited electronic configurations, and we need to find these coefficients theta. And once we find them, we can calculate the ground state electronic energy. So on modern quantum hardware, with a short coherence time, we cannot evaluate energy fully on quantum computers with methods like quantum phase estimation. And nowadays, the most common approach is the quantum classical variational quantum Eigensolver method. So here is the flowchart of how it works. So we start with the fermionic Hamiltonian, map it to qubits, generate initial trial state on a classical computer, then prepare it on a quantum computer, measure the energy, and then using the classical optimization loop and variational principle, we find the key variational energy, which is always bound by the real ground state energy. So this is how we compute the electronic energy. What about the gradients? So the gradients we compute numerically using Hellmann-Feynman theorem and finite differences method, where the Hellmann-Feynman theorem allows us to not recompute the wave function at the displaced geometries and optimize the wave function only at the central point. And for each time step of AMD, we need one VT optimization to obtain energy, and we need to compute two matrix elements using finite differences to calculate forces, and then we can propagate positions and velocities. So if we were to do this using a brute force approach, we would need to perform a BQ loop at the central point to compute the energy, and then to calculate the gradients, we would need to get the energies at the displaced geometries, which would require another two VQ loops with optimized, separate optimized variational parameters, which is quite costly, and it's essentially 3 times the effort compared to just the energy calculation. When we use the Hellmann-Feynman theorem, things get better. We don't do the full VQ evaluation at displaced geometries. We just take the variational parameters, optimize the central point, and just do a single quantum measurements at displaced geometries to get the energies, and so that we compute the gradients. So the problem with the numerical gradient is obviously that the accuracy. So to get the accurate numerical gradient, you need to set the displacement parameter to a small number on the order of 10 to the minus 3, 10 to the minus 4. And as is the case with quantum measurements, you always have some noise when you measure it, either stochastic or noise from the quantum device. And therefore, when you get these independent energy errors at displaced geometries, by dividing it by a small number, you amplify those errors. And to reduce the error, you would need to perform much more quantum measurements. And in a lot of cases, it is cost prohibitive. So the way we deal with this is we use the correlated sampling technique. So we calculate the energy at the central point using VQE, and then we take that measurement of all those polystrings, and we simply use them to compute energies at the displaced geometries. We only recompute the classical 1 and 2 electron integrals. And so this significantly reduces the cost, because we don't perform any measurements at displaced geometries. But more importantly, we what we have here is that the errors of energy displaced geometries are not independent anymore, and therefore we expect the accuracy of numerical gradients to be much higher compared to the uncorrelated sampling. And the reason why this works is that for different points for displaced geometries, the polystrings do not change. Only these coefficients that depend on one and two electron integrals change, and therefore we can use the same measurements and to get the higher accuracy. So the simulation types we do in this study is we start with the state vector simulator, which is basically a readout of the wave function without any noise from the stochastic nature of quantum mechanics. And when we use the QASM simulator, which simulates that stochastic noise, where the wave function, when we measure it, collapses to one of the possible states, and we need to perform multiple measurements to get statistics to get the required accuracy. And finally, in simulations on hardware, on top of stochastic noise, we also have noise from quantum devices, and this requires error mitigation. We test our method on HET system using Qiskit for quantum simulations and PySCF for classical electron integral evaluation. And as I already mentioned, we use the unitary coupled cluster with singles and doubles using minimal basis set. For H2 molecule, this UCCSD is equivalent to full CI because it only has 2 electrons, and its all configurations are covered by the single and double excitations. We use parity mapping, which allows us to do the symmetry reduction, which reduces the number of required qubits from 4 to 2. And in addition, we use the qubit tapering technique described in this paper to further reduce the number of qubits to 1. So this is the circuit for a 1 qubit system, which is quite elementary. That's why we decided to also include the same simulations for a 2 qubit system and look at the effect, how all these extra gates affect the accuracy. So first, energy is computed on a QASM simulator with only stochastic noise, where we did full VQE at every step. So here we did it with different number of shots from 8,000 to 512,000 along the potential energy surface. This black line is the chemical accuracy, and from here you can see that to be consistently within chemical accuracy, we need to be in the range of around 256,000 shots. So to calculate the gradients, we need to choose the parameter d, and these are the calculations of the gradients using state vector simulator without any noise, with different parameters d. As you can see, the smaller values have smaller errors. However, even the largest error for 0.01 value of d, the error is on the order of 10 to the minus 3 millihartz per Bohr. And we argue that the errors coming from the stochastic errors are much larger. So here are the calculations on a QASM simulator using a million shots. And here there is no dependency of the error on the displacement parameter, and the errors are on the order of 1 millihartz per Bohr, which is 3 orders of magnitude larger. And on this graph, this is root mean square error for the gradient for different number of for different values of d. And as you can see, there is no correlation between the d parameter and the error. And this is we attribute this to the use of the correlated sampling technique, which allows us to avoid these problems. So hardware simulations. So we use the IBM Vigo machine, which has 5 qubits, which we picked due to the lowest error rates. We performed the 288,000 shots for each energy evaluation, and we computed this trajectory, a single loop trajectory starting from 2 bores. And here you see the representation of a trajectory. Since the system is one-dimensional, you can represent it on a plot velocity versus position. So here the state vector simulator is orange. So this is essentially full CI. The blue line is the full VQE optimization at every step, and the green is the dynamics ran using quantum hardware, but without VQE optimization of theta parameters on a quantum computer. The parameters that are here we take from the state vector simulator. So these are optimal parameters. And here you can see the total classical energy conservation. We don't really see difference between the full VQE and the propagation with optimal parameters here. In both cases, the error fluctuates within several millihartz, and classical energy doesn't seem to deviate from the average. So for 2-qubit system, we did the same simulation, just with on a 2-qubit circuit. So here the orange and green lines are the same as were on the previous slide, and the red one is the 2-qubit system. And as you can see, due to these 4 CNET gates with error rates on the order of 1%, it results in the potential energies that are significantly higher, and the conservation of classical energy is also gets worse. And here we didn't perform any error mitigation other than measurement error mitigation as implemented in Qiskit, and we definitely see how much worse the dynamics trajectories get just by adding a few extra gates. Then the last thing I want to talk about is how can we scale to larger system size. So to validate the method, we need to eliminate the error that comes from the classical VQE parameter optimization, and also variational that's not been exact for larger molecules with more electrons. So to do that, we do the exact diagonalization. It's an point to get the exact wave function, and for each polystring, we sample matrix elements using the exact wave function instead of optimizing it with the VQE. And we sum all the matrix elements to get energies and compute the gradients. So here you can see the plot of how many shots you need to reach 1 millihartz per bore accuracy. So the blue is the brute force approach, red is the application of the Hellmann-Feynman theorem, and the green is when we use correlated sampling. And these are different molecules. the same molecule with different number of qubits are basically when you use symmetry to reduce number of qubits or not. And so there's two things you can see from here is that the Hellmann-Feynman theorem doesn't affect the accuracy of the gradients here. However, it makes the calculations cheaper. But when we, on top of Hellmann-Feynman theorem, use the correlated sampling technique, we see a drastic improvement in accuracy, and we need 3-4 orders of magnitude less shots to reach the same accuracy. And this method is also cheaper, so we need to do less measurements on a quantum computer. So to sum up, we propose a method to calculate numerical gradients on NISQ quantum hardware using Hellmann-Feynman theorem and correlated sampling technique. It allows to reduce the number of quantum measurements by 3 orders of magnitude to achieve the same accuracy. We performed the AMD simulations on quantum hardware. The larger molecules would require more qubits of better quality and additional error mitigation. And the last thing, in addition to VQE, this approach of using correlated sampling can be used to calculate gradients with other algorithms where wave function is available, for example, quantum phase estimation. And with that, I'd like to thank my advisor, Yuri, Alexeev at Oregon National Lab, my collaborators, Matthew Otten and Stephen Gray, and Aaron Jasper for fruitful discussions, and also the collaborators from General Atomics. Thank you.